My name is Ben Ku. I'm from Tsinghua University from Beijing, and today my talk is about how to deliver computational thinking to the masses. Thank you. Okay, I think I'll start now. I think I committed a very serious crime by using PowerPoint instead of using a mathematical notebook. But I was trying to copy a lot of images. It keeps crashing, so I think I have an excuse. Okay, so my topic is about how to deliver computational thinking to the masses. When I talk about masses, I mean as many people as possible. So starting from I think 2 years ago was the 70th anniversary of UNESCO. And the chief secretary of UNESCO actually announced that the education system in many countries are not even relevant to labor market opportunities at all, meaning that we are totally useless as a professor. Okay. And then this year I was attending OECD. In French, they spell OCDE. I didn't say it wrong. But anyway, that the Ministry of Education has officially announced that artificial intelligence and robots are changing educational needs, but nobody's really offering a comprehensive program from the foundation. So this is for the masses in the sense that schools are changing. So the first thing that we know is they are MOOCs. They are so-called School 42. It's totally a free program. You don't even pay for tuition. You get to become a programmer, and supposedly that this is going up in Paris and now in San Francisco. And schools are trying to push people out of their campuses, wanting them to become so-called entrepreneurs. And so-called incubators are becoming more like schools because students are pushed out of campuses, they don't have sufficient skills, and then they need to actually learn something. So like Y Combinator is a very famous so-called incubator, but they are really kind of like a school. So these things are really shifting the paradigm. The problem is that there are no way, or at least not a very, very rigorous way of teaching people how to do computational thinking. Until in 2006, Jeanette Wing, the computer science department director of Carnegie Mellon, she wrote a paper on computational thinking, define what is and what is not computational thinking. And clearly, Stephen Wolfram has been talking about computational thinking frequently. And then like 2 months ago, he wrote this article called How to Teach Computational Thinking. And then soon sent me that's last month actually, he sent me an email, said, Ben, you should be doing this. It just happens that I was actually starting a brand new course called Computational Thinking at Tsinghua. So I said, maybe I should talk about this here at this conference. So that's why I'm here. So the thing is that these people are not the masses. Both Stephen Wolfram and Jeanette Wing are the masses. They are the very normal people. They are the kind of people who knows computational thinking. But how can we actually deliver the kind of ideas they had? Jeanette Wing was very well known for model checking. I think very few people in the masses actually know what is model checking. And Stephen is a really strange guy. He's a super smart person. So they are the kind of thing they talk about may or may not be suitable for so-called computational thinking. But there's one thing that's important. Stephen's new book actually talked about the key personalities in computational thinking. And it actually connects many, many dots that people like myself can actually get into this. So now, because the topic is about how to deliver computation to the masses, so knowing here I'm in the United States, I want to give you some background information about my context. From the get-go, the last 2 years has been very transformative in China, primarily because WeChat, the biggest like WhatsApp application, started offering peer-to-peer payment. So that profoundly changed the way social dynamics works. So I actually completely stopped carrying cash and completely stopped literally moving a physical piece of money to any local stores, even on the streets. And these kind of things are, again, further fueled by the notion of blockchain, Bitcoin, and then even, as you can see, the central governments in China are very much interested in the notion of using blockchain technologies to actually issue sovereignty money. And then people like Vitalik Buterin, the person who designed the so-called Ethereum, a smart contract that actually bound itself its fiscal liability to blockchain or Bitcoin kind of currencies. He offers his own currency called Ethereum, whatever, coins or money. And then these ideas, either from the top down or bottom up, are changing the way we think about what the future money and power and also responsibility lies in. The problem is that very few people knows how to really write smart contract. Very few schools are teaching how to write smart contract. And China, knowing this is a situation, they're trying to push all schools to do maker education, get people to start doing 3D printing. If they were here learning about Wolfram Cloud, they probably will learn how to do Wolfram Cloud. But obviously, Wolfram Cloud is not very popular in China at this moment in time. But the notion of learning something about parallel computation, CUDA, or GPU programming is very popular in China. But still, just knows how to write hardcore computer science code may not be computational thinking for the masses. Let me explain why. For example, this is Larsen Delmar, a chemistry professor in University of California, Davis. About 3 years ago, he stopped asking his students to buy textbooks. He makes his students write textbooks using Wiki, MediaWiki. And within three years, he collected roughly about 20,000 pages worth of higher quality text. And then very quickly, as you can see, from chemistry, biology, geology, so every single subject is now accumulating many texts. At least 30 to 40 schools sign up, and about 7,000 students are writing textbooks for themselves. So when you start doing this kind of work, even though you are not writing source code, you are actually using computational thinking because your content is now being collected at a massive level. So recently he changed his name from UC Davis ChemWiki to LibreText. And NSF found it very interesting. So they've given quite a bit of money. And also Science and Nature actually constantly ask him to write papers about how this will revolutionize the way any other subject matter is going to be changed by network-based computational thought processes. So one of the founder of ChemWiki, Ron Rusey, is coming to China next week, and that's why I'm leaving right after this meeting, immediately flying back to China to pick him up. But we are obviously also doing that with him. So all of my courses right now are all the assignment, all of the material content is completely distributed using Wiki. So we run our own local Wiki services in our department. And I didn't go to sleep last night because my machine was hacked, so I was worried about this. But anyway, so obviously just writing Wiki alone is not enough. The National Open University in China have more than 10 million people subscribe to their MOOC kind of services. But you can imagine the traditional kind of MOOC service is literally watching a video and probably by email or by some kind of relatively static content and send some homework assignment back to the server. So the director of Open University came to me. He asked, Ben, is there a way to actually change this kind of paradigm? Can we actually have better quality of delivery and better quality of reception? So we're talking about tens of millions of people. Then, as a programmer in the past, I know there's a very simple thought processes for all programmers. You need to first write tests, which is called verification, do the right thing. And then you need to somehow test it in a real life environment, which is called validation, the VMV, the two V's we're looking at here. So obviously, if I just say VMV to the director of these two big institutions, they'll just look at me, what the hell does that mean? So I have to try to translate in three different points. The first thing is that in order to get the masses to understand what's computational thinking, we need to put them back in the richer context. Secondly, maybe people are not interested in chemistry. They are not interested in Wolfram Cloud, but they may be interested in let's say, fixing a car or running a cinnamon bun shop, right? But can they actually incorporate some kind of rigorous thought processes, some kind of computational thinking processes? The second thing about getting people to do things well and also being verified and validated as a qualified, productive member of society, then they need to figure out how to write so-called contract with each other. But it turns out contracts are very logical items. As you know, in the foundational computational science, the notion of contract, design by contract, is a very, very basic idea. But obviously, even some programmers, even myself, when I was doing this, I was not really very formally trained by this. And the third thing is, when you have all these things, you need to somehow figure out a way to constantly give feedback. In the past, especially for Chinese students, test is a very powerful element. But when you have many, many tests, if they are repeated, it's easily cheated. Therefore, you need to generate tests. More importantly, you want to make tests useful and interactive so that they're actually learning things, not just taking tests, they are actually doing productive work. So to solve these problems, I came up with a generic framework for teaching anybody computational thinking. First, front-ended with the orientation program, and is based on the cognitive foundation class. But generally, I classify all my students into 3 classes, the A, B, and C classes. The A classes people are so-called strategists, or business people, or people who believe strongly they'll never learn how to program. But these people still need to know what is computation regardless. The B class people are people who actually know computational technical structures well enough, but more importantly, they need to actually deliver the computational infrastructure to the masses through certain kind of architectural services like Wolfram Cloud kind of thing. And the third kind of computational thinking people are people in the trenches. They may be doctors, they may be neurosurgeons, they may be all kinds of other very specialized people or car mechanics. But these courses also, as you can imagine, the modern cars are so smart, it literally drives themselves. So these people, as of now, actually do need to know a lot about computational thinking. But the most important thing about this ABC school is the notion of recursion, meaning that all these orientation programs are composed of people from all 3 different classes. And then once they got into the orientation program, eventually, as they go through the process, they'll become the designer of the program. So refining the entire curriculum by themselves. So this entire school is a learning machine, is a recursive production machine for knowledge, not just the notion of teaching a particular subject matter, measuring the performance of individual student. We're talking about the entire school as an organism, and we want to make this entire school as a device that learns. And it turns out there's another program called Brian Robertson, who wrote this book about 8 years ago called Holacracy. How many people know about Holacracy? Heard of it? No? No one? Okay. So it's great. So obviously I'm showing you something new, right? So Holacracy was written by this programmer who believed that in the modern ages, in order to have really flat and flexible organization, the best thing is that everybody can figure out to become one member in a circle. And then basically by defining their scope of management, everything is going to be managed just by defining the membership, defining the rights and responsibility for people having certain membership, and also the official procedure to change the responsibility and rights of the member. So it turns out it's a generic abstract version of constitution for any organization. And according to him, there are many organizations that's running very profitable operations up to thousands of people, even sometimes millions. Even many hackerspaces around the world are using Holacracy to run this. So what I did is the very first thing coming to my classes is to either read it or actually write it. So just in August, this past August, I made the incoming student for my master's and engineering students. In the first 4 days they were in my class, and I would force them to actually completely translate the 41-page of long constitution into English, from English to Chinese using Wiki. So they are simultaneously learning how to use Wiki and editing the book, and also come up with a nicer layout as well as cover design, all in 24 hours. So literally, they are organizing their own resources using the principle of holacracy and running a autonomous and self-organizing system and serving as distributed operating system without necessarily using computer, other than using wiki. So on the other hand, it turns out computational thinking is not just about writing code. Computational thinking is about writing the controlling scripts that control resources in general. So to make it very concrete about the notion of masses, that we know that Bitcoin is a very big deal now in China. So it turns out 70% of all Bitcoin mining happens in China. The transaction, in terms of actual American dollar transaction volume, also 70% happens in China. So he happens to be a PhD student in our physics department. He's like 53 years old, but he's still a very, very interesting PhD student. So he happens to know many, many people in this community. So he organized this so-called blockchain association and got like 10 or 15 top, not all of them are in the picture, to become a instructor for my ABC school. So these people actually, some of them are the top programmer for either Ethereum or blockchain. They're actually helping me design the APC course in the 3 different categories. So they're designing 3 layers of courses, teaching people how to actually write a smart contract for investors, for programmers, and for average people. So obviously, since we're talking about computational thinking, we have to talk about what is to be computed. So the ABC course, or any courses I run, because I force all my students to use either Git or use Wiki as the data capturing device, so I can very easily capture what they did. This is done in 2014 in September, the incoming class. So this is all the Git transactions. So you can imagine all my students, even though they are not necessarily programmers, they have to learn how to use Git right away. And then I was able to capture very, very precise behavioral activity for these students. But obviously, using Git sometimes is difficult, so that I started switching over to using Wiki. This is the version control for Wiki, and more specifically, this is one of Wiki page my students learned in my Cognitive Foundation class. So I knew this person must not have copied this content directly from other places just by reading the number of changes and realizing the frequency of changes is so high, she must not have been copied the whole thing. And because I tried on the other nicer pages, and I can very quickly realize it's completely copied. And how do I know? Again, going back to this process data. So everything is evidenced, having a very precise evidence. So then you might wonder, I have 3 different kinds of classes. What do I teach in those classes? So I have 3, in this case, Cognitive Foundation, System Design and Computational Thinking, and Industry Frontier. These are tailored to 3 different groups of students. So instead of just thinking of it individually as people learning courses from me on one particular subject matter, I intentionally make all 3 groups of students, synchronize them week over week, and trying to bring out similar topics every week and make them write wiki entries. The Cognitive Foundation people actually talk about metaphors, because metaphors is known by cognitive scientists being the generic mechanism for people to have any kind of conscience or cognitive instrument. And then I actually make them to read and write about category theory while I'm getting students in the computational thinking course to talk about different kind of compiler design issues. And then the industry frontier people, because these people are focused on so-called smart transportations, smart devices, and robotics. So when they are talking about writing smart contract, I make them make references to the other 2 kinds of keywords. So then the transaction on specific sets of keyword naturally shows up in a community of about 100 people. So then over time, oops, it died. I didn't do anything. Oh, okay, Microsoft also crashed, so it must be the images. Okay, let me try it again. Okay, I'll quit Mathematica altogether. I just proved to you I also use Mathematica. I'm not a fake, right? Okay. Oh, again. What? Say, what'd you say?
I said, are you telling us to leave?
Oh, sorry. Yeah, so, okay. So this is one of the animation that we actually wrote this script using NetLogo. And some of these are coming from the real data from about 4 days of very intensive script writing, wiki entry writing. So we can literally emulate a school of about 100 people without them actually physically showing up. But obviously, we were using the actual data. The reason I showed this to you is it turns out this programming language called NetLogo happens to have almost identical sets of vocabulary because Logo was from Lisp. So many of the terms was very much similar to category theory's notion of morphisms, arrows, or functions, and also objects and things of that sort. Obviously, I'm not going to talk about category theory here. But then there's another layer of important idea I think we discovered this time. That in the beginning of this year, that I discovered this course called Nantu Tetris by Noam Nissan and Shimon Shoken. The two professors in Israel basically spent about 15 years to develop a course. They claim for people with zero background, you can build a computer from transistor and using Harvard description language, finish in the first 5 weeks a complete computer with CPU and memory designed. And then the remaining 7 weeks, you can actually do the virtual machine, compiler, operating system, and write a simple a video game like Tetris. So I was a programmer. I never knew that I know even more than 2 or 3 layers of these complexity. So I did the course myself. And it spent about 5 weeks. According to the website, I only need to spend about 5 hours per week to finish the thing. But probably because I'm getting old, I spend at least 15 hours per week to get things done. But after I got things done, I realized by knowing what are the tricks using these sets of automated tests, I was able to compress the learning curve so much faster. I was able to get my son and my poor wife to actually learn this by themselves in the next 3 months. So I haven't finished. I have to be honest. I haven't finished remaining 6 weeks. I did finish week 6. But the interesting part of week 6 is that you have to write a compiler or some kind of translator translating the 28,000 lines of assembly language directly to machine language. So I have to, again, learn a programming language to do the homework. And then knowing I'm coming here in this conference, so actually I did write the entire compiler in Mathematica. And it was successful. And it turns out to be a very enjoyable experience, but I actually probably spent about 30 hours for that. But then the interesting part of this is, then I realized that you should be very familiar with programming before you start doing the remaining part of courses anyway. But I still tried all these things on, this is not my son, my son's friend. So he came over, and I just want to show you very quickly of the video. And he was actually explaining this. I don't know what, there's no sound, but that's fine. Just imagine he's speaking Chinese anyway. You wouldn't understand a word he said. But the point being that since we started teaching this class here at Tsinghua right now, we actually realized the entire first 4 weeks of courses can be directly translating from truth table using one function in Boolean function, automatically translating to Boolean expression, and we can dump using Mathematica to solve the whole problem completely. Obviously, I didn't show them to my students until this week, after they finished the homework assignment. But more importantly, the whole point is that it turns out almost all kinds of engineering tests, regardless how complex it is, even if it is all these 7 layers of complexity, almost every layer can be translated back to some kind of compiler implementation assignment. So then I realized that even though I was doing my industrial
frontier course teaching people how to write business strategy paper, the whole process is also a compilation and also a digital publishing process. So I actually did write the homework, and actually wrote instructions for students to follow this. And this is roughly the kind of industry analysis where they would write. So it's very artistic and obviously a lot of labor involved in this. But it turns out by using a set of very beautiful template, anybody can do this. So then I realized the 3 sets of chords, the ABC chords, can be actually complementing each other. I know I only have like 3 minutes left, so I want to simply conclude the fact that regardless of any kind of homework assignment, they're actually feeding each other. On the other hand, computational thinking cannot be taught as one course. It needs to cover both the societal part, the theoretical part, the engineering part, and also, more specifically, the organizational, constitutional part, so that you can work with many other people altogether. So one of the reasons I have to come here to talk about this in Wolfram conference is that Wolfram language is one of the pure, or maybe the purest functional language other than Haskell. But in general, functions has many other aliases like arrow, morphism, functor, workflow, processes, whatever they have. But more importantly, all these ideas can be captured using these type of concrete tools that we can use every day. And it turns out, regardless of what we call them, everything has very nice home in a digital space. So while I'm teaching my 3 classes of students, I realized that I can use computational thinking's homework assignment to supplement the information for my less technically oriented students when they are writing a business report and studying the implication of blockchain to the society. And while they are talking about the big stories, enticing people to come, these people can provide great references to motivate people in cognitive foundation and other courses to know more technical details. On the other hand, to deliver computational thinking, that thinking must take place in richer context if you know the right kind of metaphor. But when you are in a very rich set of context, it's very easy to get lost. Therefore, computational thinking and specifically cognitive sciences provides you 3 explicit, simple types of morphisms, which are called ontological metaphor, spatial or orientation metaphor, and so-called system metaphor. And it turns out there are 3 fundamental types of functions in general. And then these kind of ideas can be very useful in writing compilers. And then when you're writing compilers, you have to have data to deal with. Either it's natural language text, it's hardware description language, it's Wolfram language, or any other languages. Everything must be somehow become processable data. Then these things becomes verifiable and validatable, and more importantly, then thinking can become computable if you have data to deal with. And then it turns out, whatever you are thinking, unless you write them down, nobody knows what happened. Therefore, all computational processes are just some kind of social contracts. We'll just keep refining them. Only by having refinement as a process, we know we are thinking. We think, therefore, we are, right? But more importantly, in order to know you are, you have to be social because you need to have additional brains to verify your code is correct or not correct. So to conclude, that we just recently set up a permanent engineering research institution with UNESCO at Tsinghua University. We are actually working with many African countries, and they want to adopt this. And we are working with French, the original school of School 42, Epitech, the largest computer science school in France. They're providing us with some of technical infrastructure to deliver computational thinking to French-speaking people. And just last week, I just received a grant from British Council, so I'm moving Tsinghua students to England and England students to Tsinghua to actually learn about this computational thinking and extreme learning process. And to be specific, that OECD they have this new kind of assessment for creativity and critical thinking for all citizens around the world, but they are not, as of now, adopting computational thinking. They thought design thinking might be the solution. But whatever the solution is, in order to make the masses to receive proper education, they need to have better infrastructure, they need to have a rigorous framework. So that's my talk for today. Thank you.